In this lesson, we go beyond describing surfaces and not really much else to beginning to do integrals over surfaces. And the first integral that we're going to do over parametric surfaces is to calculate their surface area. And so the idea is basically to take a parametric surface, as we see down here, and slice it into small pieces and add up the approximate area of each piece and turn that into a Riemann sum and then into an integral. But the question is, first, how can we slice something like this up into pieces, and how can we estimate its area? So we have to think about this quite a bit, and as it says there, pictures really help a lot, so we'll hope that these pictures can help us out a little bit. So first we have to remember that a parametric surface is a set of equations, is represented by a set of equations that take the parameters u and v and map for each value of u and v a point x, y, z. So it's a mapping from the two-dimensional coordinate system u, v to the three-dimensional coordinates x, y, z. And because there's 2 degrees of freedom over here, this is a two-dimensional object giving us a surface. So since the functions describing the surface are functions really of u and v, those are going to be the things that we want to slice into little pieces, much as we sliced t into little pieces to calculate arc length. So that we're also helped in that effort by, from the previous lesson, the idea of coordinate lines. So these lines of constant u and constant v show up over here on the surface as coordinate lines, and so a little patch between 2 nearby coordinate lines in u and 2 nearby coordinate lines in v, which I've sketched here in red, I've hashed it in, can be directly translated over here to the part of the surface between 2 coordinate lines, the associated coordinate lines with those values of u on the surface, and the associated coordinate lines associated with those 2 values of v. So this little red hashed square over here, it directly correlates to a little hashed object here on the surface, a little patch of surface. Now it may not be a square, it might be some curved patch, but as the size of this patch gets smaller and smaller, the edges of this thing become straighter and straighter, and we have some hope that we might be able to approximate its area. So this is the basic idea. The surface is described in terms of u and v, and so we slice u and v into small pieces of width delta u and delta v, and each of those little squares corresponds to a patch of surface, and we're going to add up all the patches. So now let's zoom in on this patch and see what we can say about it. So this patch has 4 corners. There is, say, the bottom left corner in the UV plane. That corresponds to a point little r, vector function r of u and v. That could be maybe ui and vj to be more precise. But I've dropped the i's and j's in the following. Then there's a corner, sorry about that, there's a corner on the upper left-hand side associated with u plus u and v plus delta v. There's a corner on the lower right-hand side associated with u plus delta u and v. So this corner here is this corner here. And then the upper right corner r of u plus delta u and v plus delta v is given by this corner here. So each corner in the perfectly square patch in the UV plane corresponds to one of these 4 corners on the surface, which we've zoomed in on from our larger picture of the surface over here. Now here is the key. Here is how we were going to calculate the area of this patch. We say that as we zoom in on this object, as delta u and delta v get smaller and smaller, this begins to look like not necessarily a square, but it begins to look like a parallelogram. And we can approximately model this edge here, which is probably a curved edge, but as delta u and delta v gets smaller, it gets straighter and straighter. So this edge is approximately modeled by a vector from the point r, u, v to r u plus delta u and v. Let's call that vector A. So A is just the vector between these 2 points, okay, right here. On the other hand, this edge of the curved object can approximately be represented by another vector B, which is the vector between ru comma v and ru comma v plus delta v. So we'll call that vector B, and it's defined right here. Now here's the key. As delta u and delta v get smaller, this begins to look more and more like a straight, flat parallelogram with sides A and B. And if we think all the way back to the beginning of this class where we learned about the areas of parallelograms, I told you that at one point you would need to summon the formula for the area of a parallelogram. And here it is. The area of this parallelogram, which is approximately the same as that patch of surface, is the magnitude of the cross product of A and B. So we need to calculate this cross product. But before we do that, let's simplify A and B just a little bit. Turns out that they are related to the function r in a very particular way. So we have, from a while back, the idea of a linear approximation that at some very nearby point to u and v, in particular the point r of u plus delta u, which makes up part of the definition of A, this can approximately be represented as r of u and v plus the derivative of r with respect to u, the partial derivative, times delta u. And we call this a linear approximation, which gets better and better as delta u gets smaller and smaller. Similarly, r at the value u v plus delta v is approximately r plus the partial of r with respect to v times delta v. This is another linear approximation. And in the limit, these two things become quite accurate. So then the vector A is r of u plus delta u v minus r u v, but that left-hand contribution also contains an r of u and v, and so those cancel, and all we're left with is partial r partial u times delta u. Meanwhile, the vector B similarly can be simplified down to be approximately equal to dr dv times delta v. So here we have A and B are approximately equal to these partial derivatives times these small changes in u and v, respectively. So consequently, the area of that parallelogram, which we've called delta A of the ijth parallelogram, magnitude of A cross B, is just the magnitude of dr du cross dr dv, and those scalars, delta u and delta v, come out of the cross product, and they can sit here on the outside. So this is the area of our small parallelograms, cross product of these tangent vectors times delta u and delta v. And so in the limit, delta A becomes dA, and we call this the area element. Du also, delta u becomes du, delta v becomes dv, and we have the area element, dA, can be written in most generic form for a parametric surface. Partial r partial u cross partial r partial v, take the magnitude, times du dv. So then, it's a small step to say that the total area of the surface is just the sum of all these small contributions in the limit as delta u and delta v go to 0. And so the sum signs become integral signs, and this object here becomes du dv, and so it becomes dA. So it's just the integral, the double integral of dA over the coordinates u and v. And when we write that out, it becomes the double integral of partial r partial u cross partial r partial v, take the magnitude du dv. So this formula right here is the most generic formula for surface area, and it's something that's very important that you will undoubtedly have to do in a test situation. So we have some examples in this lesson, but first, a really great example is to find dA for a parametrization associated with polar coordinates. So polar coordinates allows us to express points in the xy plane in terms of r and theta. Under the relations, x equals, and here we'll use u and v instead of r and theta, u cosine v and y equals u sine v, and staying in the xy plane, we set z equal to 0. So this is nothing more than the equations describing polar coordinates, okay? But they can also be thought of as parametric representation of the xy plane. So what is the area element on that plane? We calculate partial r partial u. It is cosine v sine v 0. And we calculate partial r partial v. It's negative u sine v, u cosine v 0. And we take the cross product. The cross product of those two tangent vectors can be found by taking the determinant of this pseudo matrix. And we get just u times k. We have I times nothing. I and j both contribute nothing because of this column of zeros. We have the k vector times cosine squared u minus negative sine squared times v times u. And so we have a cosine squared plus sine squared, which becomes 1. And so the tangent vector is just u times k. And that makes some sense, the direction anyway, because we're just in the xy plane. The tangents are in the xy plane. And so the cross product should be perpendicular to the xy plane. And indeed, that's what we see here. But nevertheless, here is the magnitude of this small vector is just u. So this cross product here is just u, and so dA is thus u du dv. This was nothing more than a replacement of polar coordinates, u equals r, v equals theta, and so here exactly we see our dA in polar coordinates is r dr d theta. So this is another way to get r dr d theta. In fact, it's a more general way. Previously, we had sketched sectors of a circle and subtracted them, and in a limit we said that this was r dr d theta. But for parametric surfaces, we may not have this kind of calculation available to us. This relied on some formula for a sector of a circle, whereas this, all we needed was these two tangent vectors to calculate it this way. So this is really a better way to calculate r dr d theta for polar coordinates. Now let's do a harder example, including the full integral. And a fun integral to do is integrals on a donut. So, of course, mathematically this is called a torus. But here we have the parametric equations for a torus. I will not derive them here, but these nevertheless are the equations for the torus. And here I have two parameters. I maybe should have used u and v, but I'm using phi and theta for my two parameters. And theta is the parameter associated with traveling around the donut in this direction, whereas phi is the parameter associated with traveling around the torus in this direction. And these two coordinates are sufficient to describe the surface of a donut. So once we have defined our surface, the calculation of a surface area integral is really pretty mechanical. It involves the same steps every time. We're always going to calculate partial derivatives of the vector function r equals these three sets of components. So r theta, partial r partial theta, I'm using subscript notation now, is going to be this prefactor times negative sine theta, comma, this prefactor times cosine theta, and here we have no thetas, and so the partial derivative with respect to theta is 0. Calculating r sub phi, partial r partial phi, I'll get nothing from these r terms, and so I'll have negative r sine phi cosine theta, negative r sine phi sine theta, and r cosine phi. So these are my two tangent vectors. I now take their cross product. I do that by setting up my determinant matrix, and I have written out the result of all these terms. We have lots of terms here, and we now need to take the magnitude of this vector, and that looks like a daunting task, but it can be simplified if we notice that all of these terms have some common factors. We have here r, capital R, the radius of the donut, plus little r cosine phi in every single term, so that can be pulled outside the vector. We also have a little r in every term, and so that can be pulled outside the vector, and we get this prefactor, and what's left is a more manageable vector. Here we have cosine phi cosine theta I hat, cosine phi sine theta j hat, And I've made one more simplification here. Here I have sine squared theta times sine phi plus cosine squared theta times sine phi. And the sine squared plus sine squared cosine squared become 1, and we're left with just sine phi. So some simplifications can be made to make this vector much more manageable. Now when we take its magnitude, this scalar prefactor can come out, and we simply have to take the square root of the sum of the squares of this bracketed vector. That's going to give us cosine squared phi cosine squared theta, cosine squared phi sine squared theta, which can be combined into this term, plus sine squared phi. Here, this becomes 1, leaving us only cosine squared phi plus sine squared phi, which is also 1. So this whole interior is just 1, and the square root of 1 is 1. And so the magnitude of that cross product is this much simpler thing here, little r times capital R plus little r cosine phi. Now we need to remember that little r and capital R, I should have said earlier, are just parameters describing the donut. It's the major radius of the donut and the minor radius of the donut, and those are fixed. Those are not variables in this problem. The variables are theta and phi. So our dA only contains one of the variables, phi, here. The surface area integral is now, we need to find bounds on theta and phi. And we look at our donut, we see that it goes all the way around the xy plane. So theta goes from 0 to 2 pi. And phi traces this whole circle out around, so phi needs to go also from 0 to 2 pi. And so we have 0 to 2 pi, 0 to 2 pi of dA, where dA is written as just calculated. And this integral is not too bad. There's no thetas in the integrand, so the 0 to 2 pi in theta simply becomes a 2 pi. And then the integral in phi gives us little r capital R phi plus r squared sine phi from 0 to 2 pi. Of course, sine of 0 is 0 and sine of 2 pi is 0, so we get nothing from this term. And we're left with just this bit right here. 4 pi squared r little r capital R, which can be written in the suggestive form 2 pi little r, 2 pi capital R. So it's just the big circumference of the donut times the little circumference of the donut gives us the surface area, which is kind of a cute result. It's of course not always true, but for donuts, it's just the product of the two circumferences gives you the surface area. So that was kind of a complicated calculation, but it shows how we calculate these surface areas, and it shows how powerful they can be. We never could have calculated a surface area using standard functions of graphs, for instance. That would have been very difficult. One last example, probably actually an easier example, but we'll do a general result and then a simple example of it to conclude. So because graphs of functions are so ubiquitous, it's not necessarily true that they are the best way of describing surfaces. I would say parametric surfaces are, but many surfaces can be described as graphs of functions. So it's worth finding the surface area integral for graphs of functions. And we can do that because, as we've seen, any graph of a function can be written parametrically. We just let x equals u, y equals v, and then z equals the function h of u and v. This is now a vector function, which means we can take partial derivatives with respect to u and v. We get 1 comma h sub u, partial derivative of h with respect to u, and r sub v is 0, 1, h sub v. When we take the cross product, we get minus h sub u minus h sub v 1, and then we take the magnitude of that to get 1 plus hu squared plus hv squared. And so the area element of the graph of a function is going to be that square root times dx dy in Cartesian coordinates. And this is true for the graph of any function h of x and y. This is a formula that is maybe worth remembering. It's relatively easy to derive, but it's common enough that it's maybe worth remembering. So example, let's take the graph of a function, z equals x squared plus y squared, and find its surface area the surface area of that portion of the graph which is inside the cylinder x squared plus y squared equals 1. So I have sketched this situation. Here is the parabola, and here is the cylinder, and we want the portion of that parabola marked in blue that is inside the cylinder x squared plus y squared equals 1. So that's going to be a unit circle of radius 1 that we need to integrate over to get the surface area of the parabola. And we go ahead and we say, okay, dA, I have my formula for dA, 1 plus hx squared plus hy squared. And in this situation, hx is 2x, giving us 4x squared. Hy is 2y, giving us 4y squared. And so dA is the square root of 1 plus 4x squared plus 4y squared dx dy. However, this problem is going to be tricky if we try to do it in Cartesian coordinates, because here I have a unit circle, and I'm going to have to calculate y as a function of x. For the unit circle, that would be, we would have something like x going from 0 to 1, and then y would have to go from negative square root of 1 minus x squared to the positive square root of 1 minus x squared, and that would be kind of a mess. However, since we're talking about circles here, the domain is a unit circle, and here I have a circular paraboloid with 4x squared plus 4y squared. I should be thinking polar coordinates, that this problem will be easier to change into polar coordinates. So let's do that. So all my x squareds plus y squareds become r squareds. My dA, I know from polar coordinates, becomes r dr d theta instead of dx dy. And if I look at this object, it's inside a cylinder of radius 1, and it goes all the way around. So r goes from 0 to 1, theta goes from 0 to 2 pi. Those are much easier bounds than in Cartesian coordinates. So our integral becomes transformed. I now have an integral from 0 to 2 pi in theta, 0 to 1 in r. My dA becomes this square root, which is now 1 plus 4r squared, and my dx dy becomes r dr d theta. And this is particularly handy because I have a r squared inside the square root while I have an r on the outside, so I should be thinking u substitution. So I let u equal 1 plus 4r squared, du is 8r dr. This is standard calculus 2 at this point. We change variables from r to u, and so we have to change our limits. When r is 0, u is 1, and when r is 1, u is 5. We have 1/8 of a du, and this becomes the square root of u. So when we integrate, we get 2/3 u to the 3/2, and it's a matter of plugging in numbers and simplifying fractions to get our answer for the surface area.